everyone, thank you so much for clicking onto the video. Today we're going to be learning about the effect of temperature on rate constants. So our learning objectives are to explain the effect of temperature change on the rate of a reaction and hence the rate constant. And then we're going to look at the Arrhenius equation, so the exponential relationship between the rate constant and temperature. And we're going to be able to we're also going to be able to determine the activation energy and A graphically using this equation derived from the Arrhenius equation. Now we're going to talk about the Arrhenius equation, and what this equation calculates is the rate constant K. So we get an exact value for the rate constant. So there are two things to note. The first is that the bigger the rate constant, the faster the reaction. And that's because for reactions we normally have rate equals K times something. So that means that if this K is a lot bigger, then the rate will be a lot faster. And the second thing is that the higher the temperature, the faster the rate of reaction. And that's because when we increase the temperature, the particles move with more kinetic energy, so there are more collisions per unit time. More of the particles have that activation energy required to successfully collide. So that means that there are more successful collisions per unit time, so the rate of reaction is faster. And now I'm going to quickly go through this equation and what all the letters stand for. So first we have the rate constant, which is K. And this, the units of this depend on the order of reaction. And then this A is the activation energy. And then T is the temperature. And that's measured in Kelvin. The activation energy is measured in joules. And then this R here is the gas constant. And that's measured in joules per mole per Kelvin. And that's usually given as 8.31 because it's a constant. And then A stands for the Arrhenius constant. And this has the same units as K. So it depends on the orders of reaction again. And then this E is a mathematical number, and this is the exponential. And this can be used on the calculator by typing in shift and then ln. Now we're going to look at some graphical analysis. So we have this equation here. If you don't know how I got this equation, then go back to the video where I worked out the activation energy required from Arrhenius's equation. And so we can plot a straight line graph from this equation that we have here. And that's because we know that straight line graphs have the general form y equals mx plus c. And so we can make this into the form y equals mx plus c. So we have y, and we can make ln a equal to c, and then we have mx. And so this gives us that the y would be equivalent to ln k, m would be equivalent to minus EA over R, the x would be equivalent to 1 over t, and c would be equivalent to ln a. And so the graph we get would be like this. So on the y-axis we would have ln k, and on the x-axis we would have 1 over t plotted. And then the graph should look something like this, because the gradient, which is the m, this is the gradient, is negative. And so this gradient would be equal to minus EA over R. So the way you find activation energy would be to find the gradient of the graph. So that would be to draw a little triangle here and divide the difference in the y by the difference in the x. You do the gradient multiplied by minus the gas constant. And then this point here, this would be our ln A, because C is the y-intercept. And so that's how you can find the Arrhenius constant. So you would unlog it to find A, and you can find the activation energy by doing gradient times by minus the gas constant.